Friends, welcome to lecture 43 of Advanced Steel Design course. We are now continuing the problem of unsymmetric section. And we are trying to locate the shear center. Okay. So, this was the unsymmetric section we had. We located the UU and VV axis. We first located the CG of the section, that is, we found out Y bar and Z bar. Then we located, we computed IY, IZ and YZ, and then computed alpha angle and located UU VV axis. Then we are in the process of finding out the shear center. Then we attempted to take moment about point A, where V2 and V3 are concurrent and no moments will be created. So, we wanted to only find V1. To do that, we wanted to find out the distance V bar, because we are using or we are transforming the problem to a principal planes. So, we wanted to find out V bar, and this was the expression we had to find out V bar. So, V bar is 16.48222Z. So, then we substitute that V bar here in this equation and get V1. So, now V1 will be, see here, Vt by Iu integral. Now we can say this will be for length of 20. So, I can say 0 to 20, right. So, see here we have A, which is Z dz, that is what we are looking for. Z dz is what we are looking for. So, Z dz, so let us say Vu Vt by Iu 16.482 plus 0.22 Z dz. That is what we have here, is it not? V by Iu T Z dz V bar. V bar is already here. We will evaluate this integral and we will find out this as Vt by Iu 16.482 Z square by 2 plus 0.22 Z cube by 3 of 0 to 20. If I do that and T is 2 millimeters, V1 will now become 0.121 V. Now, we will take moment about this. So, we will draw this figure. Now, we will take moment about A. So, V, we will call this as EU, right. V into EU will be equal to, this is V1. So, V1 and this distance okay, 38. So, already we have V1 with us. So, V1 is 0.121 V. So, V into EU is 0.121 V of 38. So, V goes away, EU is 0.121 into 38, which is about 4.59 millimeters. So, this is about 4.6 millimeters. Okay, that is how we can find out. So, friends, when you do a problem of unsymmetric sections, one need to locate the principal axis before proceeding to locate the shear center. That is a very important point which we must remember. Okay. We will do one more example. Say example 4. Draw this figure. So, the problem is locate the shear center of the given figure. Okay. Section like this. Of course, this has an axis of symmetry which I am marking here. Let us mark the dimensions. I think we will. We will mark the dimensions of this. First, let us mark the center lines. Then mark the shear flow. Let us say this is V4, this is V3, this is V2, this is V1. Let us mark this dimension as B1 and this dimension as B. There is also B. This is 45 degrees. Of course, this is also B1. The section has uniform thickness T. This is a point which we call as point A, and the shear center will be located somewhere on this line. Let us say this is my shear center C. The vertical force will pass through this and we will measure the distance of this center from the point A as offset of shear center, which is E. Okay. So, from this figure by symmetry we know that V1 is equal to V4 and V2 is equal to V3 because of the dimension similarity. Okay. So, we will cut a section. Let the section be cut from here at a distance z, and let the thickness of the section be dz, and of course, this thickness is already given as t. We are looking for the CG of this from here. Okay. This is my y bar for piece number 1. Okay, for piece number 1. So, now V1 is given by integral 0 to B1 V by IT A y bar of piece 1 into D. So, A of piece 1 is T into Z, dA of piece 1 is T into dz, y bar is B sin 45 minus B1 sin 45 plus Z by 2 sin 45. So, B sin 45, let us say you see here. So, we are looking for this distance. Okay. B sin 45 will be this. B1 sin 45 you will be reaching here. Then if you do, this is Z, Z by 2 will give to the center, you get this value. So, which will be B minus B1 plus Z by 2 of sin 45, which is y bar. Okay. Substituting, let us get V1 as integral 0 to B1 V by IT dz into T dz B minus B1 plus Z by 2 of 1 by that is sin 45. Integrating and substituting the limits, we get Vt by root 2I B1 B1 square this is not B1, this is B, B1 square by 2 minus B1 cube by 2 plus B1 cube by 6, okay, which will now become Vt root 2I B B1 square by 2 minus B1 cube by 3. Therefore, we get V1 as Vt B1 square by root 2I of B by 2 minus B1 by 3, which is identically same as V4. Okay. Now, be taking moment about the point A, I do not have to work out V2 and V3 because they are concurrent about the point E. Okay. So, by taking moments of all forces about A, V2 and V3 are concurrent and hence no moment. So, there is no need to calculate these two. So, directly I can use V1 and V4, but there is an issue here. V1 need to calculate I of the entire section. So, this I is the moment of inertia of the whole section. So, that is a tricky thing here. Okay. So, let us do one by one. So, we need to find I of the whole section. Okay. So, now to find I of the whole section, or x dash, and we call this small axis as UU and VV. We know, and this dimension is of course B, and this thickness is T, this angle is 45 degrees. Okay. We know IUU is TBQ by 12 and IVV is BTQ by 12 and IX dash X dash is IU cos square theta plus IV sin square theta, where theta is 45 degrees here. So, I can say it is TBQ by 12 cos square 45 plus BTQ by 12 sin square 45, which will be TBQ by 12 1 by root 2 the whole square plus BTQ by 12 1 by root 2 the whole square, which becomes TBQ by 24 plus BTQ by 24. This is IX dash X dash. Okay. Now, I have an axis here which is XX. So, now I can say IXX will be IX dash X dash plus AK square, which will be TPQ by 24 plus BTQ by 24 plus AK square, which is B into T of the distance. Okay. You know, XX axis actually not here, we should mark it here. Look at this figure, X axis is the tip. Okay, let us mark it here. XX. So, which will be B by 2 sin 45 the whole square. Okay. So, which will give me IXX as TBQ by 24 plus BTQ by 24 plus BQT by 8. Okay. B cube T by 8. So, it will now become 4 TB cube by 24 plus BT cube by 24. So, we should say TB by 24, 4B square plus T square is my IXX of that arm. Okay. Let us do it for the arm B1, because we have done for this arm. Let us do it for this arm. Let us draw. So, this is my B1. I am looking for an axis which is XX. Let us also mark centroidal axis as UU and VV for this, and we call this horizontal axis as X dash X dash, and the dimensions are, of course, this is B1 and this is T. Okay. So, now we can say IU will be B1 T cube by 12 and IV will be TB1 cube by 12. So, IX dash X dash will be IU sin square 45 plus IV cos square 45, which will be B1 T cube by 12 1 by root 2 the whole square TB1 cube by 12 1 by root 2 the whole square. So, IX dash X dash will be B1 T cube by 24 plus TB1 cube by 24. So, now IXX will be IX dash X dash plus AK square. We can apply this. So, which will be equal to B1 T cube by 24 plus T B1 cube by 24 plus B1 T of, the angle is connected here, is how it is connected, and this dimension is B, is it not? So, I should say B sin 45 minus B by 2 sin 45 the whole square. That is my K square here. Okay, let me copy this equation. So, IXX will be now equal to B1 T cube by 24 plus TB1 cube by 24 plus B1 T B by root 2 minus this is B1, okay, B by root 2 minus B1 by 2 root 2 the whole square. Is it okay? Simplifying, I get this as B1 T cube by 24 plus T B1 cube by 24 plus B1 T of B square by 2 plus B1 square by 8 minus B1 by 2, which will be B1 T cube by 24 plus T B1 cube by 24 plus B1 B square T by 2 plus B1 cube T by 8 minus B1 square T by 2. This is my Ixx of the first piece. So, now we can say Ixx of the whole section will be, let us say, the piece number, this value, I am copying it here, okay, which I am writing it here, TB by 24 4B square plus T square, okay. Let me rub this, then I will copy this down, which I will write it here, plus B1 T cube by 24 plus T B1 cube by 6 plus, I am simplifying, okay, plus B1 B square T by 2 minus B1 square T by 2, the whole into 2. Now, I draw this figure take moment about A. This is the point A, okay. So, we can say V into E will be equal to V1 into B, right, because that is the distance of V1 from here, and that is same as V4, so into 2. So, now I have V, I have V1, I have B. So, find E. So, for example, if B1 is 40, B is 70, T is 2 millimeters, okay, you can find E, right. So, friends, in this lecture we learned 2 examples. One, we learned how to work out the shear center for unsymmetric section, and we have seen the steps involved to locate the shear center. We have also learned one more example, and in this example we learned how to choose the point to take moment of all internal forces to find the shear center. So, we can choose this point very advantageously so that our computational effort can be reduced. So, friends, with this we will be completing the discussion on shear center. There are many more problems available in the textbook referred by me for this course. Look at those examples and try to solve them. We have also seen curved sections, we have seen asymmetric sections, we have seen symmetric complicated sections, which are all very common sections used in mechanical systems as well as structural systems. For example, this kind of sections are used for crane rails. These kind of sections are used for pipe racks, because you get more space to put the pipe. So, these are all rectilinear shapes, but arranged in such a fashion they create very complicated geometry for computational purposes. So, you should be able to look into these and practice more problems, so that you are clear about solving them from the first principles. Okay? Thank you very much and have a good day.